In this video, we would like to learn about the output of LTI system when you have complex exponential as the input of the LTI system. As shown in this example, you have an LTI system. The input is x of t and the output is y of t. And suppose the input output relation is given by this expression that y of t is x of t minus 3. So the output is basically a delayed version of the input. So this is a system which delays the input, right? It gives you an output, and of course if you are interested in finding out the response of this system, let's try to find out the response of the system, the impulse response of the system. So when we say the impulse response of the system, we want to give an impulse at the input. So suppose we give an impulse delta of t at the input, and we are interested in finding out the output, which is actually the impulse response. So if our input is delta of t, based on this input output relationship, we can write our output, which we would refer to as the impulse response of the system, because the input is an impulse. So the output would be x of t minus 3. So x of t is, now our x of t is delta of t. So x of t minus 3 means x of t minus 3 is basically delta of t minus 3. So we can see that the output, we can see that our impulse response is basically delta of t minus 3 for this LTI system. So let's see its response when the input is this is how we can find out the impulse response of a LTI system. Now suppose we have an input which is a complex exponential. Specifically, suppose our input x of t is given by e raised to the power j to t. Suppose our input is a complex exponential, x of t is e raised to the power j 2t. Suppose this is the input, and we are interested in finding out the output of the system. So keeping in view our input output relationship, we can write y of t, which is x of t minus 3, and based on it you can write j2. Instead of t you have t minus 3. Now t minus 3. So if you solve it further, you would definitely come to know that your output y of t is basically e raised to the power j minus j6, right? E raised to the power j to t. So if you observe closely, your output is basically the input, same as the input, multiplied by a factor e raised to the power j6, which can be written as e raised to the power the h of j2, because our for our LTI system, as we have learned in the previous video, that the output y of t is basically same as the input, and actually instead of writing x of t, say when the input is a complex exponential, the output, we had this form previously. So if the input is a complex exponential, the output is same as the input, and this is the function h of s. So we have actually this form, and we can see that our output, which we just determined, our output is basically same as the input, and it is h of j times the input. So writing it, I can write it in a similar fashion. We can say that our output, this one, is h of j2 times the input, e raised to the power j 2t, right? So it's in a similar form as we have discussed in the previous video. Now you can see, you can find out this hj of t, as we saw in our previous video, that if you are interested in finding out h of s, it is basically related to the impulse response of the system, and it is actually h of tau e raised to power minus s tau d tau, right? So this is how you find out h of s. So if we are interested in finding out h of j2 using the same expression, you should be able to find it out, right? So let's try this one. So we are interested, we already found this impulse response h of t, right? So we already have h of tau available with us, which we just found above, that h of tau is basically delta of tau minus 3, right? So just replace t by tau in the above equation. So we already have found this one. So if we are interested in finding out h of j2, right? Or instead of directly writing this way, let me first of all, I would like to say that, okay, if I'll repeat that expression, that our h of s is basically from minus infinity to plus infinity, h of tau and e raised to power minus s tau d tau. This is how to find. Now we have s is equal to j2 in our expression, in our above expression, and we already have expression for this one. We need to find now we can rewrite our h of j2, which would be from minus infinity to plus infinity h of tau, or instead of h of tau, I would like its value delta of tau. Delta of tau is actually tau minus 3, delta of tau. This is h of tau, this is h of tau, sorry, h of tau and e raised to the power minus j2 tau d tau. This should give us h of j2, right? So let's try to find out this h of j2. Now keeping in view, let me evaluate this integral for you with the help of let me recall your previous concepts of delta of t. So if you recall your concepts, let me do it here on the left, on the right hand side. If you have delta of, if you want to write this, if you want to draw this function, or only this one, the first one, because this is the product of two functions, the delta of tau minus 3. So if you plot delta of tau minus 3, suppose this is 0, this is 3, 0, delta of tau minus 3 is basically an impulse which is at 3, right? This is an impulse which is at 3. This is your delta of tau minus 3. Now this is multiplied, this impulse is actually multiplied with this exponential, and you already know that if you have any other function which extends from minus infinity to plus infinity, any function from minus infinity to plus infinity, right, and you multiply this, the first one with this one, the multiplication, the product would be only at instant tau 3, because for the rest of these time values, the first function delta of tau minus 3 is 0, and if you multiply anything with the 0, although the second function which we see in this figure, it is from minus infinity to plus infinity, but the first function is 0 in all these time instants except for tau equal to 3. So basically this product will have value only at tau equal to 3, and that value would be the whatever is the function value at tau equal to 3. So now we have the function, the second function, which is which comes in the multiplication. This is the second function which I would like to write it over here. This is our second function. If this function exists from minus infinity to plus infinity, the only value which we are interested in is at tau equal to 3. So the only value of this function which would generate some non-zero product value, this product value would be non-zero at tau equal to 3, right? So this tau value, we can replace it. We can say that, okay, this product, this particular product, delta of tau minus 3 e raised to the power minus j 2 tau, this will have value only at tau equal to 3. So we can replace here, we can replace this by 3, right? So let me rewrite my equation from which I have to find h of j2. So we are actually interested in finding h of j2 from this expression, from minus infinity to plus infinity, delta of tau minus 3 e raised to the power minus j 2 tau d tau, right? This is our expression. H is I think this is not minus, here it is plus e raised to power j 2 tau, right? So this is the we are interested basically in this value. So if you observe it closely with the help of, let me see my previous values which we have computed earlier. So we have these values, okay. So tau equal to, we have to come, this is minus s tau, sorry, I have to write this negative sign here. I have to write this negative sign because we have this we have e raised to the power we have this one, e raised to the power minus s tau. So let me write this negative value. I was just forgot it, whether it is negative or not. So let me write here a minus. So it's a e raised to the power minus j 2 tau. So we have to find h of j2. What we can do, we know that the product, this product has a value of delta of tau minus 3, this value, and it would be multiplied with basically the only value which is non-zero is j 2 times 3. Instead of tau, I would write the value here, tau 3. Only this product is non-zero only for this specific, at this specific instant. Now what I can do, now you can see this integral e raised to power, we can just write this outside the integral, e raised to power minus j 6, and we can write our integral delta of tau minus 3 d tau, and you know that this integral basically is equal to 1 because it is the integration of a delta function, from minus infinity to plus infinity, which is actually equal to unity, and you are left with e raised to power minus j6. So this is your h of j2. Now this is how we find the values. This is how we find h of j2. It's very similar. Now you can compare it with the generalized equation. You can compare it with the generalized equation that your output y of t is basically the input which is e raised to the power j2t with the function modified by h of j2, right? And we already found this h of j2, which is e raised to the power minus j6 j2t. So our output y of t of LTI system is basically a complex exponential, the same as the input multiplied by the same as the its input multiplied by e raised to power h of j2 or e raised to power j6 minus j6, e raised to power minus j6. So this is the example of LTI system. You can also think about another as the second example. Let me give you another example. Example 2, and in this case we consider another x of t, which is suppose cos of 4t plus cos of let me write cos of 4t plus cos of 7t. Suppose this is the two sinusoids, the summation of two sinusoids. Our x of t is the summation of two sinusoids. So if this is the input, what would be the output? Of course, you can straightforward write the output x of t minus 3. So you can say that my output y of t would be equal to cos of 4t minus 3 plus cos of 7t minus 3, right? You can straightforward write your output. It's an easy example, but let's try this one, the input. Let's try this one by converting it into complex exponentials. So x of t, we can write our x of t using the Euler identity. I hope you are familiar with the Euler identity. Let me write it over here, e raised to power j theta, or let me write the cos of theta in terms of complex exponential. So you can write cos of theta as e raised to power j theta plus e raised to power minus j theta over 2. So this, using the Euler identity, you can derive it from there. So let me write x of t in this form. So if we using that expression, if we write cos of 4t, so cos of 4t we can write e raised to the power j 4t plus e raised to power minus j 4t over 2. And similarly we can say e raised to the power j 7t plus e raised to the power minus j 7t over 2. So if you see the input, actually the input is complex exponential, again in the form of exponentials. Half, we can rewrite it, minus j 4t, then we have half e raised to the power j 7t plus half e raised to the power minus j 7t. So you can see that the input to this LTI system are these exponentials, right? So if we have exponentials as the input, we would expect that our output, and now let's write the output also. This is, we have written this input using Euler identity. So let's write our output, which is y of t, this one, in the form of complex exponentials, right? So let's try this one. So let me see, let me write this output y of t. If we write the output y of t, we can say that okay, our y of t is basically e raised to the power j 4t minus 3 plus e raised to the power minus j 4t minus 3 over 2. I'm writing it from here, right? And then you have an additive term again, Now the second one, I'm writing this one now. E raised to the power j 7 t minus 3 plus e raised to power minus j 7 t minus 3 over 2. Now you can rewrite this equation. So let's try to rewrite it. This can be written as half e raised to the power j 12 with e raised to the power j 4t plus, now I have just written this term. Now let me write another term from here, right? Just a separate one. So this is half e raised to the power, here we should have minus 12, right? Here we should have minus 12 j, yes, and here j. Okay, now from here we have e raised to the power plus j12 e raised to the power minus j4t. It is minus j4t, and you can also write it. You can also write it here. The third one. Now I would like to write this one. So this is e raised to the power minus j21 e raised to the power j7t, and half is there. And if I write this one, that would be below here half e raised to the power j21 e raised to the power minus j7t. Now if you compare it with your input signal in the first one, you can see that you have an input e raised to the power j4t. Half e raised to the power j4t is the first term, right? In x of t, half e raised to the power j4t. If I bring it a little bit below, you can see your x of t here. Now this is your x of t. The first term of x of t is this one. Let me bring it here. The first term of x of t, this one is okay, I have to mark it using red marker. This is your first term of x of t. So your first term of x of t appears here, and it is this is your h of j4, right? The first term is as it is in the output y of t, and similarly you have a second term. Second term is also here, and you can find your second term here. This is your second term. Similarly you have your third term, same, and your fourth term is also here, your fourth term. Now you can if you try to simplify this one, you can clearly see that you can just make a simplification. You can just collect the related terms, and you can write this equation. Back. You can bring it back to this one, 4t minus 3 plus cos 7t minus 3. You can bring it back to this equation, your y of t. So basically our outputs are the input times some h of is in the same form, h of j4 here. We have h of j4 here, and you can find your h of j4 using the same expression which I have done in example number 1. So I would like you people to go in details of this example and practice it, so that you come up with the response of LTI system when your input is the complex exponentials.